Morning, everyone. So here I'm going to talk a little bit about using machine learning to actually model RNC. So the objective here is actually to make use of the machine learning algorithms capabilities to actually understand complex, high-dimensional data relationships to help us understand whether are there any other external key factors that drive RNC. And ultimately, what we want to do is actually to have a model that is able to forecast RNC severity. And having such a model will actually help us make more informed decisions for disease management. So to do that, we looked at extracting climate data from the NIWA climate station. We also use topographic information such as elevation and slope derived from using remote sensing. And we also use RNC field observation data that we extract from the forest health database and site observation. And from these data sets, we actually managed to extract and derive over 130 features that we use to successfully build a spatial climate area-based model for predicting RNC given predicting the severity of RNC for a given location and its associated climate conditions. So to actually go about how we go about understanding what are the key factors that drive RNC, we look at how the model actually uses the features for prediction. So here we first massage and clean the data into a format where the machine can actually analyze, and then we train the model on the data. Once the model is trained, we actually ask the model to generate a feature ranking. So this feature ranking is basically a ranking of how the machine perceives the importance of each feature for predicting RNC. So using the ranking, we then focus on the top 15 important features, and we actually extract the data using those features and correlate them with our RNC field observation. So our feature analysis exercise sort of affirms some of the observations field observations that we observed previously, such as moisture playing a key role in driving RNC. But not only that, we also managed to identify interesting climatic and topographic features that would show signs of contributing to driving RNC. So features such as wind speed, distance to coastline, slope, and elevation. We also observe a strong data relationship when correlating historical information back to RNC observations. And this sort of gives us an indication of how we can better model RNC moving forward. Next, we actually sort of test the prediction capabilities of the model using data that we have withheld from the model during training. And here we can see that the model is actually able to predict the seasonal cyclic expression of the disease that we observe in the field from our field studies earlier on. Having said that, we also found out that our model is still not very accurate when forecasting this RNC severity for areas that we have no information about, and the gap between the accuracy here actually is a strong indication of that we do not have enough information yet to actually have build a generic forecasting model. So moving forward from here, we need actually more high quality information on disease severity. We see that remote sensing actually plays a key role here to actually not only help us gather large-scale information of disease severity, but also more importantly, unbiased and consistent data as compared to if you send field operators out into the field.